Hi everyone, I'm Maria Nadestad, and in this video I wanted to talk a bit about how to make better bioinformatics software. A lot of this might apply to making any kind of software, but I want to specifically talk about bioinformatics because that is something I have a lot of experience with, and making several bioinformatics tools. And I made a lot of mistakes, or I did a lot of things in my software during my PhD that I have since learned better ways of doing things. And so I wanted to share some of these tips with you that I've learned over time. And this goes for everything from just your pile of analysis scripts all the way up to building software that you're going to actually publish as its own methods paper, and that other people can use. So some of the top things that I wanted to share. First of all, why should you focus on writing good software? So first of all, software is a great skill that you can keep building during your PhD and beyond. And even if you're not doing a PhD, just building software skills as a biologist, a bioinformatician is extremely valuable. It's very powerful because you can automate a lot of things, and I don't have to say much more about that, obviously. Like, software engineering is also a very lucrative career in itself. So when you combine that with your biology, you get these skills that are also highly transferable across many different fields in biology, but also, you can take it with you to a different biology lab if you're moving around in your career a little bit, which I think we all do. And software is something you can take with you anywhere. Your software engineering skills you can take with you anywhere, but you can even take it with you outside of biology. And I have had lab mates who have left biology entirely and just taken their skills to tech companies or startups instead and worked on totally different things. So you have a lot of options. Software engineering is also very near and dear to my heart. It's one of the biggest areas that I have grown in, and it's by far the best thing I've done for my career, getting good at writing software. There's no way I would have gotten either of my industry jobs without the software tools that I have written myself and the ways I've presented them at conferences. So let's talk about some of the things that I have learned, have gotten better at, have learned to do a little differently. And these are like really high level things. So there's basically 5 major things here. So the first one is start using Git and uploading to GitHub as well immediately, even for your pile of analysis scripts that you're like starting out with, where you're just experimenting on like, oh, how do I like use the aligner to align the NGS data and stuff like that. Even at the very beginning, just like write down what you're doing. Write down your scripts, write down, as if it's a lab notebook, just like keep track of what you're doing and put that in a Git repo, put it on GitHub right from the beginning. This is helpful because you can back up your work, and it's like basically free using GitHub. You can do private repos, and there's various restrictions around that, but mostly you can do things for free at this point. And it's also really helpful to document your analyses for when you finally publish the paper. I found that for my big paper out of my PhD, it was a little difficult to find all of the initial analyses I had done. And I ended up like quickly redoing some of it to make sure that the code I was including with the paper was completely accurate. I tried to redo some of the analyses just to make sure it was right, but I could have just kept better track of it right from the beginning and made sure that all of the steps are well documented. So if you document what you're doing right from the beginning, put it on Git and GitHub, you don't have to worry about that. And a bonus here is also tracking your own progress over time. If you're storing everything you're doing, you're like regularly saving what you've been doing, you can also see how you've been improving and how your analysis has changed over time and when it changed, so that when you have some file that was created on a certain date, you can go back and be like, oh, what did my analysis script look like on that date? So it helps you kind of with some of that provenance, figuring out where your data came from, how it was analyzed. So really valuable. And of course, those skills are also some that you'll use for building actual software. So there's a lot more that Git and GitHub can do, but even just for your analysis scripts, you should be using it. And when you're building software as well, definitely be using it right from the beginning. It's also really rewarding to like commit something that you have done and be like, check, I have like done this one feature and it is finished, at least for now. So the second thing, and this I've actually always been really good at, is dog fooding. So this is what we call when you're using your own stuff while you are building it. Dog food, I think, refers to some case where a company was selling dog food and they would like try eating it themselves or something. At least that's like the vague idea I've heard somewhere, but don't quote me on that. At any rate, we call it dog fooding, and it just means to use your own product. So I've been really good at that because I built all the software for my own use. So while I was doing my own analyses, I would find that some software was needed, so I would build the software and I would continue to use it for analyzing my main project's data and to continue the project. So that is something I highly recommend doing. In fact, I don't really recommend that you build software unless you have a concrete use case for it, and unless you can find ways to use it yourself, because otherwise you're going to be missing a lot of the features that are needed. Like, you won't know what to build. So the third thing that I recommend that you do is unit testing and maybe integration testing, but at any rate, testing your code. And I would especially recommend that you try something called test-driven development. So this is not always a good idea, and you'll find lots of discussions about this online, but in case you haven't already been spending a bunch of time in the software engineering ecosystem of the internet, I will briefly summarize out of my own experience. So I built an application called SplitThreader in my PhD. This was one of the first things I did with visualization as well, but it had some complicated graph algorithms, or they were like nicely simple and elegant, but the underlying data was complicated. So I initially wrote these algorithms and got them working, but I needed to at one point port them from Python to JavaScript. Back in Python, I had added unit tests afterwards, and I had caught maybe some issues. I don't actually remember if I caught any bugs when I was adding the Python tests, but I used PyTest for this. This is a unit testing framework in Python. And if you're not familiar with unit testing, it's like saying, okay, I have this function, let me give it an example input and the output that I expect and check that those are the same. There are many different other types of unit tests, and you can like test it throws a certain error, you can test all sorts of different things. But when we're working with algorithms, it's really nice to have these tests because you want to be able to have some toy examples so you can actually test whether the software is behaving the way that you want it to. Is it actually returning the correct answers? So there are a lot of things like in software engineering where people are talking on the internet and it's like, oh, why would you need unit tests for these things? But when you're doing algorithms, you're doing computations where the inputs and outputs are not trivial. Like the internals of the function is not just like, oh, you should like set a certain value. Okay, let me write a unit test to check that the value has been set. Like that's pretty simple. And maybe you can test all of that with like integration tests or something more high level instead. And let's not worry about that. Like there's a lot of things I'm not necessarily testing, but I would definitely always test the complicated functions, the ones that, like in SplitThreader's case, it was graph traversal algorithms. I wanted to make sure that in my toy examples that I could in fact find point B going from point A when they were connected in a toy example graph that I was drawing on paper, had encoded into the test as like the graph that it should traverse, and then seeing if it could actually get there. And then I would, make ones where A and B were not connected, and I'd make sure that it couldn't find a path there. And I would like have a few different toy example graphs and different points on the graphs and see if my functions that I had written could find them and get the correct distances and so on. So these types of things are really important to test. So if you're building anything where a function's contents are not trivial, where you might have edge cases, and this is a lot of things that we're doing, I would highly recommend that you do testing. So test-driven development is like doing unit tests, but you write the unit tests before you finish making the functionality itself that you're testing. And so when I was porting the functionality I had about graph traversal and split threader from Python to JavaScript so that I could use it in a web app, I wrote the unit tests first. I drew toy example graphs with A and B positions and so on, and I drew them on paper, and I calculated by hand how to get from one point to the other, what the distances should be, and so on, so that I had the right answers. And then I wrote the functionality that would actually get there. By doing it by hand first, it also gives me an intuition for how the algorithm would work. Like, when we're building these algorithms, we often end up doing things like that by hand first to work out how the functionality should work. So then we may as well take that and turn it into concrete test cases at the same time. And then that means that when you finally write the functionality, you will already have the tests for it, and you can make sure that it actually works the way you expected it to. Because it can be really difficult to translate it from a concept to the code. And that's a really important thing. No software engineers are perfect. We expect that we are going to make mistakes. And the most important thing is that we find ways to mitigate the effects of our mistakes, to catch them early, to make sure that the effects are not too catastrophic. So it's really important to have unit tests. I know I've been ranting about unit tests for a while now, but it's important. Fourth, making your software more modular, breaking it up into pieces that are individually usable, and making your software just usable in different ways. So let me explain with an example. So one of my pieces of software, Assemblytics, I had created as, at first it was a bag of scripts. I just had written a few different scripts. Some were in Python, some I had adapted from a Perl script that my advisor had built, so I had just changed the Perl script a little and just fit it in, and I put all of them together into a bash script. And then I put a web app around it, and it's very nicely, easily usable as a web application. But the back end of that web application under the hood is a little embarrassing now. So there were a few things that I wanted to change about this. So one problem with it is that some people wanted to run Assemblytics from the command line, not just on the web. So the way that I initially solved that problem was to copy the entire repository. Don't do this at home. Copy the entire repository, or copy the pile of scripts and the bash script that put them all together, copy those into a different GitHub repo, and just hooked it up so that you could call that from the command line and it would look decent. Anyway, so now I had two different repos, one for the web app and one for the command line app. And now when there was one user request to change a specific parameter, which I had hard-coded before for real reasons. It it was good to like control as many parameters as possible, but someone really wanted to be able to change that parameter. So I added that option, I think, in the web app, but I didn't copy the functionality over to the command line application because I was busy. I had a full-time job and stuff by then, which did not include maintaining my old software. So this is another thing in academia, like when you kind of move on with your life a little bit, it's hard to keep maintaining the software. So you also want to have a plan in place for what you're gonna do, like how much time can you spend maintaining it afterwards. And I do keep maintaining my software, but you know, it's hard sometimes to find time to later. For instance, I had to port it from Python 2 to Python 3, and that was something that I put off for many months because it's, you know, I would have to like test it, it's all working again. And this particular application doesn't have unit tests, so I would just have to test it with real data, and I was afraid to break something. So you want to make it more easily maintainable by having tests and things like that, so that in the future, when you don't remember how everything works, you can still see whether it's working when you like update a package, like update some dependency, or have to port from Python 2 to Python 3, or whatever it is that you have to do. If you have to add a feature because someone really needs it for an important project or something. Yeah, you want to think a little bit, how can I make this easier for myself in the future? So anyway, so now we have these two repos, and some functionality is in one but not in the other. So now they've diverged from each other. They like forked and have diverged further, and that is not good. We don't like that. We don't like copying code. Copying code is pretty bad. We have this principle in software engineering, in coding, I guess in general, called DRY, dry principle. It's don't repeat yourself. So copying the code was bad. The reason that I did that initially was just as a quick fix to the problem. What I later did, when I then had to port all the code from Python 2 to Python 3, I was like, okay, I need to clean up this because I am not happy with the way it's set up. It's kind of embarrassing. I'm a better software engineer now. I wouldn't do this if I was doing it today. So the thing that I would do instead, and what I ended up doing, which took a bit more effort but was worth it, was I collapsed them back together again. And like one of them is just a wrapper around the other, right? You have the command line app, then you have the web app that puts like the nice glossy finish over it. So that's like much easier to work with because some people will want to use your thing as a command line tool. It is much nicer to have a few different ways that people can use your tool. Now that brings me to the other thing that I did wrong about Assemblytics, which is that I should have probably, added unit testing, but also I should have tried to do everything in it in just Python. I had written my own scripts in Python, but if you might remember, I just mentioned that I had taken a script in Perl that my advisor had written, and I did not rewrite it, I just added to it in Perl, and then I strung them together in a command line app. Now, if I had put them together, I could have put everything together in Python. I also had some R plots, and I even used some awk and other command line tools to stitch a few different output files from different scripts together and pass them into like an R script that then would create a plot. And I think I had more than one R script that created different plots. So it was a little complicated. And it's not ideal from a software engineering standpoint to link together so many different languages when you don't really need multiple different languages. If I was doing it from scratch, I would have unit tests, I would do it in Python, I would basically make it all one big Python script, including the plotting. I would just use Python libraries for the plotting as well, and I would stitch it all together in Python, and so that makes it usable as a Python library. Now it's also usable as a command line app, and it's usable as a web app. So you have different kinds of ways to use it. And that is what I would recommend if at all possible. If your app does need to be more complicated, you can't put it all into Python as a pip package and stuff like that, or in R is like a crayon package, that's also great. But if your app does have to be more complicated, then I would suggest that you build a Docker image for your application and make sure that it contains everything that you actually need to get your application working. So the way that you test that, and you have to test things, right? This is one thing I think I've mentioned a lot in this video already, is testing. So when you're, like, it's really nice if you can build a Docker image. Now take your Docker image and try to use it from a clean virtual machine on a cloud platform. So all the cloud platforms, I think, have some kinds of free tiers and so on, and see if you're able to install your program from the Docker container. Because if you don't, then it might only work on your computer. And this is why bioinformatics tools are so hard to install. So the fifth thing I wanted to talk about is a little bit of an umbrella thing, but that is to use your peers. This is something that I didn't learn to do until I was in industry. So I had already built several software tools entirely by myself, but I had never had a code review done or done a code review for someone else until I was in industry. And this is something that I would probably change if I was starting over again, because you can learn a lot from getting your code reviewed by other people. Even if they don't know more about coding than you do, it is still nice to look at your code as someone else is going to look at it and see, oh, some of this looks kind of ugly or not understandable. You want your code to be readable. Readability is extremely important for code. You want to be able to put some comments in different places to explain some of the complicated parts. You want to define your inputs and outputs of all your functions and what types they should be. And what is each function doing? There should be a lot of annotations and things like that in your code to help people understand what the code is doing and how it's doing it. Because reading the code is almost never enough to help understand some of these things, especially for all the complicated algorithms things that we're doing in bioinformatics sometimes. And all the statistics and stuff like that, it just becomes kind of a mess if you don't explain what you're doing. And then when you look back on it later, you have no idea what you were doing either, because future you is like a different person. I look back at some of my code, and there are lots of comments, but many of them are me commenting out print statements. So that's not good. That's how I used to debug. I mean, it's still how I debug, but now I get rid of the print statements afterwards. So yeah, you definitely want to clean up your code, have someone else look at it, and have them, try to understand the code a little and give you some suggestions for improvements. It can be really helpful to get a second pair of eyes on what you're doing. And then when you review other people's code, you can also learn tricks from them, and they can recommend tricks to you as well. And then you just, you learn more about different ways of doing things, and that's always helpful. The other thing that kind of goes along with code reviews is design reviews. When you're trying to design an overall application, like you're deciding which languages to use. Is it going to be a command line tool, a web app, a library, stuff like that? What is it going to do? What is it not going to do? What are the features, the main use cases, things like that. You want to write all that down in a document and share it with your colleagues. Not just your advisor, or your boss or whoever you have, but all of your peers as well, and try to get their views on it, because you can learn a lot from discussing these decisions more, and you might end up with much better decisions at the outset of a project that can save you from some of the problems, like the aforementioned experimentation with web apps that should have also been command line tools, that should have also been Python packages, and so on. I have learned a lot about software engineering from working with other people, and I would highly recommend you do that even if it's not built in as into the requirements of your role. I wanted to share just one additional tip for general bioinformatics work, so that was our 5 things. But as a bonus tip, one thing that I've noticed I would often, in my early days of doing bioinformatics, would do analyses and I'd have some folder and it had a bunch of files in it that I had created, but I would not really be able to remember what tool I ran with what parameters to produce some of these files. And it's very easy to basically lose track of all of that. So, we talked about putting your pile of scripts on GitHub. That's a really good start, but I would also recommend while you do that, that you leave a little trail of breadcrumbs for yourself in each folder that you're dumping files into. Just put a little README where you put whatever information might be helpful for retracing your steps later. There, on the command line, there isn't a tool called history. So if you just type in history on the command line, you will see what your previous commands were. And even if you just like output that to a little README file or something in your folder, that's already a good start. It helps you retrace what you just did to, produce those files. You might have to go a little more detailed than that. Maybe you didn't just do them, or maybe you want to link to a specific script in your GitHub at a specific time point, for instance. Like you just committed it in your pile of scripts and you want to just like link to that. So just like leave yourself some information in that folder about where the files came from, and you will thank yourself so much later when you're trying to figure out if these files are still relevant, if they're still with the newest version of the code, if they're like which reference genome they're on, or which parameters for the aligner you used, and all of that. So yeah, you will thank yourself later. I hope this was helpful to some of you. I hope it was helpful to all of you, but I do recognize that it's a long video. So yeah, tell me in the comments if anything was surprising or interesting to you, or like what you got out of this video. Yeah, I will see you guys around. All right, bye.